I'm Ahmed. I'm a Google software engineer, and I've worked on Beam for 3.5 years now. And I think I became a committer like 2 years ago-ish. And for the past year and a half, we've been working on creating the Iceberg connector for Beam. You've heard about Iceberg a lot today already, but yeah, just one more talk about that. So we'll go into a little bit about what Iceberg is, even though you've heard about it already. Then we'll talk about the different sources and sinks we have. We have the Iceberg sink and a source and a CDC source. So we'll go through each of those and their capabilities and some examples. And this whole presentation is just like a public service announcement about this new connector and how to use it and all that. And then we'll end with some like potential areas of improvement that we're looking at. So yeah, what is Iceberg? Iceberg is an open table format, which basically means it's just like a specification or a blueprint for how to write data and how to write metadata about that data to create a logical table. And it's built to handle a lot of like data, large scale data sets. So yeah, it's like a layer of data files. And on top of that is a bunch of metadata that like allows a bunch of advanced features that we'll see soon. And one important thing too is that metadata allows Iceberg to maintain a versioned history of the table. So any change you make, whether it's an insert or a delete or like a change in the structure of the table, the schema, the partition spec, each of those operations creates a snapshot of the table that you can then roll back to if you want to. So here's the famous diagram for Iceberg's table structure, and I'm not going to go into it. And there's a bunch of really nice videos on YouTube about what it is and how it works. Here's one of my favorites. If you have the slides later on, you can go and look at it. Okay, so a colleague of mine asked me why should I use Iceberg instead of like some other like database out there, and some of the reasons are it's highly interoperable, so it's open source. It's when you use it, you're not locking yourself into one vendor, one cloud provider, or one engine. It's also highly scalable. It's very efficient for queries, and you can evolve the schema. You can add or remove a column without having to rewrite the whole table. And like I said, it can do time travel. You can go back in time. It has asset transactions, and one of the most important pieces too is it's a very active community. They have engineers from all over the tech sector, and it's very, very active. So let's jump into the connectors. And I just want to make a announcement that this is like all of our connectors that we'll see soon are offered as managed transforms. There's a managed API that holds all these transforms, and Cham will talk about this in an hour, I think, in this room. So I recommend you guys to look at that one too to see why we chose this design. And all of the configuration properties for the sources and sinks that I'm going to talk about can be accessed here in this link. So yes, let's go into the first IO we have. We have the sink, which obviously writes to tables. It creates namespaces and tables as needed, and you write to it using Beam rows, and the sink can infer the schema of the table from the data. And you can also provide the partition spec or like a list of partition fields that it will create the table with. And we also support writing to dynamic destinations, which means that a record's values determines its destination. And you can write to like many tables using one instance of the IO. So let's go into a little bit about how this works with the dynamic destinations. Say we have a record that has these 4 fields: airlines, origin, destination, and duration. And you want to write to a bunch of tables, and you give it a template that says, I want to write to this namespace and this table based on the data that's incoming. So the sync will take your record and basically just like simply substitute in the values from the record into the table and write to that destination. But say, for example, you only included airlines and origin for the sake of determining where the record should go, but you don't actually want to write those columns in. Then you can provide this keep property that will tell the sync which columns you actually want to keep to write to the table. And it will just drop the other columns. Or you can do the opposite of that and like specify which ones to drop, and it might make sense depending on your use case which one you want to use. But both work the same way. So here's an actual example. You're writing to Iceberg with the managed API with this configuration. They have the table with the template, and we're saying drop these fields and create the table with this partition spec, with these partition fields. And we support all partitioning transforms. This is identity, and you have month and bucket and year and so on. There's a bunch of other ones. And it will just create the table with that partition spec and write to those locations. Like it will create this hierarchy as it writes. And this is just like this is not unique to Iceberg. This is like also in Hive and all this stuff. It's just very, very good for querying the table. It helps the engine figure out where the data actually is. And since this is a batch sync, it will write all these data files and then do one single commit operation, which creates one single snapshot. Now for streaming, you obviously need a streaming source into your sync. And you can specify at which frequency the sync should commit files to the table. So roughly at this frequency, the sync will create snapshots of the table. So one problem that we have when we're streaming data to Iceberg is that if we're writing way too fast, we'll have way too many small data files everywhere. And that's not really good for the read side because it has to like scan all these files, open all of them, and it's just not efficient. So one small mitigation we have in our sync is that you can increase the interval at which you're writing, which will buffer data more, and then write to it when it has accumulated more data. So you have like larger data files, smaller amount of them. But the downside of this is that as you're writing, you're buffering more data in state. So it might be more costly on your pipeline when you're writing. It might make sense to you, it might not. It's not a final solution. The actual solution is to actually like compact your data regularly to maintain your table. That's not something we have right now, but it's something that we're looking to add on to the streaming sync to like continuously compact as you're writing. So yeah, here's like the example with streaming. We just added that one more property. Now we support Iceberg syncs and sources for Java, Python, YAML, and SQL. And here's the Python example. And you'll find that the configuration properties are the exact same from language to language. Here's Python's using the B managed write API, writing to Iceberg with this configuration. And if we look at YAML, it's the exact same thing, same names. And you'll find that's one of the reasons why we use the managed API to do things here. Now for SQL, it's different, obviously. And this might be a little bit more familiar to some people here, like SQL language. We have to first create our catalog, then tell Beam to use it. Then we can create the table with this schema of type Iceberg, partitioned by these fields. And this is the actual fully qualified like table name or table path. And you're telling it to write at this frequency. This is for like a streaming write with SQL. And then finally you're inserting. Catalogs are a new piece in Beam SQL. We just added it recently in 2.66 to support this use case. So yeah, now moving to the source. We support data filtering with predicate pushdown and column pruning with projection pushdown, which basically means that any data filtering or column pruning, we do it at the scan level. We don't do it after we've read the whole table. So we save that time and effort. So for example, if you bring back our partition table and we say that we're only trying to look for flights in February, we use the Iceberg API to determine which directories we should look at and which ones we should skip. And it just makes querying a lot faster and more efficient. So yeah, here's the example for Java. Now it's instead of managed write, it's managed read to Iceberg. With this configuration, we provide a filter statement that is SQL friendly. And we have keep and drop as well to say like which columns you actually want to read. So that's Java. This is Python. Same thing. This is YAML. For YAML, these two fields are coming in the next release. It's not out yet, but the read is still available. And this is SQL. This is like the most familiar to people here. But it does the same thing. All of the filtering and column pruning are done at the scan level. And finally, we have the CDC source. For streaming use cases, it polls the table at certain intervals and processes the snapshots that it finds. So say you're writing to a table that is, you're writing to a table over time, and the CDC read will basically do a poll at each of these intervals, and that's how it goes. It just processes the snapshots that it finds. Now and just to give a notice, this is only available for append only snapshots. We don't so this isn't really like a fully CDC read thing yet. We don't have we don't recognize deletes or updates yet. Just appends for now. And it's available for batch and streaming reads, and you can tell it to read at a specified between a timestamp boundary or a snapshot boundary. So you can say, I only want to read between last week and today, or like last week and whatever, or between like specific snapshots that you want to read between. For batch, here's an example. You just say like, I want to read from this snapshot to this snapshot. Or you can say from timestamp to timestamp, or from timestamp to snapshot. You can interchange it. For streaming, you just have to set streaming to true, and then optionally give it a pull interval at which it will perform a table load, table scan, The default is 1 minute, but you can change it however you want. And for the streaming, for this example, we're telling it to read from this timestamp, which was yesterday morning, and it will continuously read forever from that point on. Okay, so that's it for our IOs, and some future areas of growth that we're looking into is expanding our CDC capabilities to recognize updates and deletes, but also create a sync for CDC writes. We're also looking into compaction, whether it's batch or continuous compaction at the end of your streaming pipeline. And also other administrative functions like cleaning up orphan files, expiring snapshots, rolling back your table state, and so on. And then finally, some performance benchmarks, like specifically for streaming, running them, releasing them, making them public on the Beam website. And yeah, that's it for this presentation. If you have any feedback, here's how you can contact me or create an issue on the GitHub repo, or I keep my eye on the Apache Iceberg Beam channel. If you want to send a message there, I'll be available. We're looking for feedback for our IOs, and that'd be really helpful. So yeah, that's it for my presentation. Thank you very much.